and welcome to my channel. My name is Malika Marathe and I'm a 12th grader who loves math and I'm an international lawn tennis player. So today we're going to be talking a little bit about the Taylor series. So first I'll be telling you about the Taylor series and what its applications are. Next we'll be deriving the formula for the Taylor series and then we'll be solving a couple of problems together. Hope you enjoy the video.
So to put it simply, the Taylor series is a good way to convert a non-polynomial function like sine of x into a polynomial. Okay, if I tell you to add two terms, say the natural log of x and sine of x, where do you even start? So the Taylor series can make problems like this much by converting them into polynomials, and then you can add up the polynomials and you should get a pretty good answer. So here I have the graph of cosine of x, the one in purple here, and using the Taylor series I could actually find the value of the polynomial value of cosine of x, which works for values of x close to 0. So as you can see, the graph of 1 minus x squared over 2 is pretty similar to the graph of cosine of x near x equal to 0. So you can write near x equal to 0, cosine of x is similar to 1 minus x squared over 2. And here what I've done is I've put in the value of x as 0.2, and here we have the value of cosine of 0.2 equals 0.980066577. And replacing x equal to 0.2 in our polynomial function, which is 1 minus 0.2 squared over 2, we get 0.98, which is a pretty good approximate. And this is basically one of the ways the Taylor series can help you. So moving on, we're now going to find out how to get to the formula of the Taylor series. So, okay, we have a function f of x, which is a power series. So a power series can be represented by a function f of x as a bunch of powers of x minus a. So I'm going to write this as c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed plus c4 times x minus a raised to 4, and so on up till infinity. Okay? And here we have a radius of convergence, which means that the series converges for values of x around the center A, which are no further than r, and r can be infinite or 0. Okay, so we are going to take this expression and evaluate it at a. So x equal to a, f of a equals c0 plus c1 times a minus a plus... But wait, isn't a minus a just equal to 0? So does that mean all the terms after c0 equal 0? That's correct. So we have f of a equals c0. So this guy here is responsible for the value of f of a. Okay, now we're going to take f of x and find its derivative. So f prime of x equals, well, c0 disappeared, so we have c1 plus 2 times c2 times x minus a plus, here we have 3c3 times x minus a squared plus 4c4 x minus a cubed, and so on. And we're going to go ahead and evaluate this at a again. So f prime of a equals, well, it's equal to just c1, right? Because all of the terms after it equal 0, since we have x minus a in each of the terms. So now I'm going to go ahead and find the second derivative of our function f of x. So we have f prime prime of x equals, c1 disappears, so we have 2c2 plus 3 times 2 c3 times x minus a plus 4 times 3 c4 x minus a squared, and so on. And obviously we're going to evaluate this at a again. So we have f prime prime of a equals 2c2, and the rest of the terms become 0. We're going to go ahead and find the third derivative of our function. So f prime prime prime, f triple prime of x equals, well, this is equal to, well, 2c2 here disappears. We have 3 times 2 times c3 plus 4 times 3 times 2c4 times x minus a. So 3 times 2 c3 plus 4 times 3 times 2 c4 times x minus a, and so on. And we're going to evaluate this at x equal to a. So therefore, f triple prime of a equals 3 times 2 times c3. Let's go ahead and find the fourth derivative of our function f of x. So f to the fourth derivative of x equals, when you derive this, this becomes 0, and we have 4 times 3 times 2 c4, and then plus we have the rest of the terms. And evaluating at x equal to a, we have f to the fourth derivative of x of a equals 4 times 3 times 2 c4, and that's it. There's no terms after this. And now to summarize all the values that we just wrote, we have c naught equals f of a, c1 equals, let's see, f prime of a, c2 equals, here we saw c2 equals f prime prime of a over 2, f prime prime of a over 2, c3 equals f triple prime of a, as we saw here, over 3 times 2, c4 equals f to the fourth derivative of a over 4 times 3 times 2. I now ask you, what is the value of Cn? Pause the video and take a moment to think about it for yourself. So Cn equals f to the nth derivative of a over n factorial, right? Since we have 1 here in the denominator, 1 in the denominator here, we have 2 factorial in the denominator for C2, 3 factorial here, 4 factorial here, and so on. And this works for all values of n, because, well, f to the 0th derivative of x is just f of x, and 0 factorial is 1. So this works perfectly for C0 as well. And so we can formulate all of this in the following theorem. If f of x has a power series representation at x equal to a, at a, then f of x is given by, and here we have f of x equals to the sum from n equal to 0 to infinity of Cn times x minus a raised to n. And since we have our value for Cn here, we're going to put that in. So we get f of x equals to the sum from n equal to 0 to infinity of f to the nth derivative of a over n factorial times x minus a raised to n. And this is basically what we call the Taylor series. And when the Taylor series is evaluated at 0, we get f of x equals to the sum from n equal to 0 to infinity of f to the nth derivative of 0 over n factorial times x raised to n. And this is basically what we call the Maclaurin series. And so that's it. This is basically the Taylor series and the Maclaurin series. And the Maclaurin series is also a Taylor series, except it's only evaluated at a equal to 0. So this is basically what a Taylor series centered at 0 looks like, which is also the Maclaurin series. And now let's solve a couple problems. Find Taylor series for sine x centered at 0. So a Taylor series at 0 is a Maclaurin series. So what they want us to find is the Maclaurin series for sine x. So we have here f of x equal to sine x, right? So at 0, f of 0 would be sine of 0. And we need to find the derivatives of this function, right? So f prime of 0 equals cosine of 0. F double prime of 0 equals negative sine of 0. F triple prime of 0 equals negative cosine of 0. F to the fourth derivative of 0 is sine of 0. So this is a loop. This keeps repeating itself. And the values are sine of 0 is 0, cosine of 0 is 1, negative sine of 0 is 0, negative cosine of 0 is negative 1, and we have 0 here again. So these 4 digits keep repeating themselves over and over again. So we're going to use this to substitute into our Maclaurin series. So for reference, I have here the Maclaurin series here, and we're going to use, these are the 4 repeating numbers, so 0, 1, 0, negative 1. And we're going to use those in our Maclaurin series. So f of 0, well, sine x equals, so f of 0, which is 0, plus f prime of 0, which is 1. So 1 over 1 factorial x, which is just x, plus f prime prime of 0 over 2 factorial times x squared, which is 0 because f prime prime of 0 is 0. And then we have plus f triple prime of 0 over 3 factorial, which is, so f triple prime is negative 1, so this is minus 1x cubed over 3 factorial, plus f to the fourth, which is, so f to the fourth, now we go all the way back here, which is 0. So f to the fourth derivative of 0 is 0, plus f to the fifth derivative of 0 is 1, times x raised to 5 over 5 factorial. So we have x raised to 5 over 5 factorial, plus f to the sixth derivative of 0 is 0 again, so plus 0, and then we have negative 1, so f to the seventh derivative of 0 is negative 1, so we have minus x raised to 7 over 7 factorial. to infinity. Okay? And if you see here, I notice a couple of patterns here. So first of all, I don't see any even numbers here. It's all odd numbers. So this is actually x raised to 1 over 1 factorial. And the second thing I notice here is these numbers. The signs are alternating. So here we have a positive sign. Here we have a negative sign. Then we have positive here again. And then we have negative. So we can actually predict the next terms. And so sine x would be x minus x cubed over 3 factorial plus x raised to 5, this one here, over 5 factorial minus x raised to 7 over 7 factorial plus x raised to 9 over 9 factorial minus x raised to 11 over 11 factorial plus x raised to 13 over 13 factorial. And you get it. So on. Right? So this is the Maclaurin series for sine of x. Okay, so now to write this expression into a simpler form, we can use sigma notation. So we can write sine of x equals to the sum from n equal to, well, we have 1 here, so let's write 1 to infinity. And I'm going to have a negative 1 here, right? Because we are alternating between a negative and positive signs. And I'm going to raise this to the power of n plus 1, because if I put n equal to 1 as here, over here we need a positive here, right? So negative 1, so here n equal to 1, so negative 1 raised to 1 plus 1 is negative 1 raised to 2, which is 1. So we have a positive here. And then when you plug in n equal to 2, you get the next term as negative. So what this does is basically it takes care of the alternating positive and negative signs. Next we have x, of course, and we are going to raise it to 2n minus 1. Why 2n minus 1? Because 2n minus 1 will give you an odd number every time for each and every value of n. So this is perfect, right? Because we don't have a single even number here. And in the denominator, we're going to put 2n minus 1 factorial. Why? Because the denominator is always the same as the exponent. So this is our Maclaurin series for sine of x. And yep, that's how you find the Maclaurin series. And now I want to show you something very interesting. So what does this series really mean? I've actually graphed this on a graphing calculator to show you what it looks like. So here I have this blue line you see here. This is sine of x, and this red line is x minus x cubed over 3 factorial. So this is just the first 2 terms of our Maclaurin series. And as you can see, this is pretty close to the value of sine of x, especially near x equal to 0, right? Next, I have here sine of x in blue, and in red, x minus x cubed over 3 factorial plus x raised to 5 over 5 factorial. As you can see, it has a longer range, right? So here we have, it's till around negative 2 and positive 2. So, well, if you see here, there is a big difference between their ranges. So this means the more terms you add, the closer to the value of sine x you'll get. And over here I've added one more term, which is negative 2. to 7 over 7 factorial. And as you can see, it's closer to sine x than before I added this negative x raised to 7 over 7 factorial. I've done one more, which is I've added x raised to 9 over 9 factorial and subtracted x raised to 11 over 11 factorial. And this is very, very close to the graph of sine x. So this is what the Taylor series can do for you, and I find this really fascinating and amazing. Okay, so the next one is write the Taylor series for f of x equals 3x cubed plus 4x squared minus 2x plus 1. So we're going to evaluate this at f of 0. So, well, let me just write this down. F of x equals 3x cubed plus 4x squared minus 2x plus 1. And if you evaluate this function at 0, you get, this becomes 0, 0, 0, 1. So f of 0 is 1. Then we find f prime of 0, which is 9x squared plus 8x minus 2. And this evaluated at x equal to 0, we get negative 2. Next, f double prime of 0 equals 18x plus 8. Evaluated at x equal to 0, you get 8. F triple prime of 0 equals 18. And evaluated at x equal to 0, you get, well, 18. And f to the fourth derivative of 0 equals, well, if you derive 18, you get just 0. So this is 0, and then all of the terms after it equal 0. For our convenience, I've already written down all of our functions and also the Maclaurin series. So we're going to start by inserting our functions into the Maclaurin series. So here we have f of x equal to, well, f of 0 is 1, so 1, plus f prime of 0 is negative 2 times x over 1 factorial plus f prime prime of 0, which is 8 over 2 factorial times x squared plus f triple prime of 0, which is 18 over 3 factorial times x cubed plus, and then the rest of the terms are 0, so we can just stop here, which is, so f of x equals 1 minus 2x plus, well, 8 over 2 factorial is 4, so plus 4x squared plus 18 over 3 factorial is 18 over 6, which is 3, so plus 3x cubed. But wait a minute, isn't this equal to what we started with? 3x cubed plus 4x squared minus 2x plus 1. It is. Wow. Why this happens? That's because the Taylor series is used to convert a function into a polynomial. But this function that we started with over here is already a polynomial. So the Taylor series of a polynomial is a polynomial. Pretty interesting, isn't it? So that's all for today, guys. I just wanted to give you a basic introduction to the Taylor series and the Maclaurin series, of course. I hope this video helped you. I hope it was informative. And thank you so much for watching the video. If you like my videos, then please like and subscribe to my channel. Thanks, guys. Have a good day.